Hi, this is Tom. So this is a lecture for our macrodynamics class, and I'm going to begin from where we left off. So let's see what happens. Okay, so yesterday we talked about the permanent income model. We talked about competitive equilibria, and we did some examples. And I'm going to revisit one of our examples and just extract some more things from it. And that's how we're going to begin. And then we're going to go on to look at a version of the permanent income model later today, in which the income process is a random process. So there's shocks hitting things. And we're going to use a small extension of formulas that we already have to characterize this. And we're going to get a very famous model. Okay, so here we go. So remember yesterday we had this example. So we had two consumers. They have identical preferences. Let's go. So they have identical preferences. So here they are, our standard preferences. They're identical except for one thing. Person one cares about what he or she gets, and person two cares about what he or she gets. We have the same discount factor, and we put the same utility function. We could easily change that. Okay, so each consumer has a single intertemporal budget constraint that we're making like this. So here, we've already guessed at what the competitive equilibrium prices are. And we computed them yesterday, actually. Okay, so these are our prices, and that price is for all t. That symbol means for all. This symbol right here. Okay, so here we go. So we're going to do our example. We're going to assume that person one has endowment 0, 1, 0, 1, 0, 1, 0 for t even, 1 for t odd. Person two is going to have endowment 1, 0, 1, 0, 1, 0. So looks like I changed this from yesterday. Now I've made person two the person who's endowed early, and person one is endowed a little bit late. I've read this as yesterday so that the total endowment for the two people is 1. Okay, so now I'm going to immediately jump into, as we said yesterday, this is rigged to get this permanent income result. So I'm immediately going to get this permanent income result at this person because the utility function is concave. The person wants to smooth consumption. So we're going to get the result that the person is going to be able totally to consume to smooth his consumption. So CI is the consumption, constant level of C for person I. So as yesterday, we're just going to compute C1 and C2 using this formula, using formula star. And what we got was, this time we get C1 equals beta over 1 plus beta, and C2 equals 1 over 1 plus beta. And these add up to 1. We see that C2 is greater than 1. So here's what we're going to do just for a little while today, right here. We're going to compute the implied asset trades in a sequential setup that would support exactly the same outcome. So instead of doing things with a single budget constraint, as we did here, we're going to do it with a sequence of budget constraints. And we've seen before several times that those two formulations end up being equivalent. Their equivalence, by the way, was noted by Kenneth Arrow in a very famous paper that opened up a lot of possibilities for formulating things either sequentially, like this, or once and for all. Okay, so now we're going to formulate it sequentially, and we're going to let ATI here now be the assets at time t that person I brings into period t. And there's going to be one of these. There's going to be one of these now for t equals 0, 1, 2 forever. And we're going to initialize 0 assets for both people. That's what we're going to do. So now all we're going to do is we're going to, we already know, this is going to be a big guess and verify. We already know that C1 is equal to beta over 1 plus beta for all t. And we know that C2 equals 1 over 1 plus beta for all t. So all we're going to do is we're going to substitute those two numbers, those two quantities, for I equals 1 and 2 into that budget constraint. Okay, so for person 1, and when we substitute, we're going to solve for a sequence of A's. So that's what we're going to do. So what we're doing is a little subtle. We're going to use the equivalence between formulating this problem with a budget constraint once and for all, as we did yesterday and above here. That's going to be the single budget constraint. Let's write it down again, which was this. That was the single budget constraint. Down here, it's going to be sequential. We'll call this sequential because it involves a sequence. So we're going to take here's our strategy going to be. We're going to take the consumption. So we know that they're equivalent. Why? Because we can just appeal to results that we had earlier. So we're going to use that equivalence. We've already computed the consumption there. We know the endowment because we made it up. So now we're just going to solve this equation for the AT sequences that have to support the above allocation. So here goes. I'm just going to do some math. So A11, I just substitute in. I get 0, 0, because that's his initial assets. That's his initial income. I have to subtract off his or her consumption, and I get that. So I solve, I get A1 over 1 is equal to minus 1 over 1 plus beta, which means that what the person does is he borrows beta over 1 plus beta. But in the next period, he has to pay beta over 1 plus beta back plus the interest rate. And that gives him 1 over 1 plus beta. So this is what he owes. That's his debt. And then for A21, we do it again. So we plug in this here. Now he has income. Now he consumes the same. We solve this, and now what he does is he ends up having 0 assets next period. So what this person ends up doing is, we can extrapolate this out to other T's. What this person does is he ends up borrowing the first period because he doesn't have anything, repaying it, having 0 assets at the beginning of the second period, and doing that for the rest of his life. So his debt oscillates between minus beta plus 1 plus beta and 0. So guess what? Person 2 better do the opposite. So let's verify that independently. So person 2, well, we just go through the same steps. A1, 2, 0. What this person does is he has income now, but he's actually is going to consume not his entire income, but 1 over 1 plus beta. So this person is going to end up, bringing into the first period 1 over 1 plus beta. So what he does, he or she, he lends beta over 1 plus beta. He lends it to the other type of person, and then he's repaid this. So this is how it goes. So it's going to turn out, this model is going to work out really well. A T1 plus AT2, those are the assets, are always going to be 0 for all T. That's going to be T equals 0, 1, 2. So what these people are going to be doing, what is this asset? It's a pure consumption loan now. We have a theory about what this asset is. It's a pure consumption loan, which person 2 ends up making to person 1, and then it gets repaid. So person 2 oscillates between those two, and that's what happens. Okay, so then I made another example that looks a lot like what we did before. So what I'm having now is person 1 is endowed early, person 2, so we're moving on to example 2. Person 2 is endowed late, so look at these carefully. Person 1 is endowed Y1 for the first T periods, and then after that is endowed 0. Person 2 is endowed Y2 after the first periods. So we're going to assume something tricky. We're going to assume this. I just made that up. You could ask, why am I assuming that? Well, it's to make my life easy. So we're going to apply the permanent income theory now. So this is the way this is going to go. You could work out this as an exercise. The permanent income theory is going to say, that's our equation for what the person consumes. And again, we're using beta R equals 1 throughout here, just like Milton Friedman did. We can compute what person 1 consumes. We can compute what person 2 consumes. But we set Y2 equal that. So it's going to turn out that C2 is actually going to equal C1. So then the exercise here is we want to compute what the asset level of person 1 is. So if we do this, we can get a nice formula. And what I recommend you do is do this. I'll post this out. We're going to use exactly the same approach that we used above. I'm going to take my formula for assets, which is this, minus, and I know what C is, CI, that's my permanent consumption, which I've already solved for. I know YT, I know this, I know A0I, and I'm just going to use this, I'm going to solve this equation sequentially. I'll have to do it step at a time for T equals 1, 2, 3, solve for ATI for T greater than or equal to 0. And if you do that, just go through these steps. This is what you'll get. So I'll post this lecture as usual. So then what we can do is we can figure out what person 1 does and person 2 does. But if we kind of stare at this, I'm going to cover that. The answer's down here. If you kind of stare at it, what better happened here is person 1 is endowed only when he's relatively young, and person 2 is endowed only when he's relatively old. So person 1 early in life better save, accumulate assets, meaning lend to the other person. Person 2 better borrow. So this person is going to, we kind of know person 1 is going to have to accumulate so many assets that if he is to consume C1 for T later in life, he's going to have accumulated enough assets to live just on his interest. And that is what's going to come through in these calculations, I hope. So person 2 is going to do just the opposite. So this is a nice example that shows sort of the structure of, it pulls out more of the structure of the competitive equilibrium that we did this year in the special case of beta R equals 1. Now, in just a minute, we're going to turn to the next part of this lecture, which is going to be about the permanent income model when we have randomness. As promised, we are now going to talk about the permanent income model in which the income process is going to be random. So this is going to be a modern version of Milton Friedman's model. So we're going to talk about a single consumer. Okay, so we're going to talk about a single consumer. Here's going to be how we're going to model that. Throughout, we're going to set beta. We're going to set beta R equal to 1. We're going to maintain that. Okay, and we're going to use a couple of tricks or methods using things that we've seen before, and we're going to get some payoff from what we've done before. So what are we going to assume for the YT process? So this is going to turn out to be very general and fit many, many things. So we're going to assume that YT is equal to GXT, where XT is the state. And what XT is going to be, XT, the way to think about it, it's the state. It's everything that helps predict future labor incomes. YT. So that's what the state is. So finding the state is an art. So, and then the state is going to evolve according to our friend, the first order linear vector stochastic difference equation. And we're going to assume, I'll move this, again, beta R is 1. We're going to assume again epsilon t plus 1 is going to be normal. It's going to be a normal vector, 0i. Oh, I've already said that, yes. Okay, good. Right here. Okay, so now that's our model for the person's income. The person's budget constraint, I'm going to write it this way. For some reason, I chose to write, instead of AT, I'm writing FT. Because I want to be like Milton Friedman and call those financial assets. So ft now is what at was in the previous couple lectures. And this is exactly the same equation that we had in the last couple lectures. So beta inverse is equal to capital R. Just remind yourself here. So next period's assets are equal to beta inverse this period's assets plus how much I save. And my labor income here is exogenous. It's exogenous. Okay. So if we work this out, it's going to turn out that we get a consumption function. And this is a version of what we worked out before when yt was not random. So the solution of the problem, so here's what the person wants to do. So the objective, the person now, well, what did we have before? This is the way this is going to work. And I can work out everything right over here. The way this works is like this. What did we have before? We had summation, what the person wanted to do was maximize this. Okay. And subject to this, I'll just write that. That's what we had. And the one difference is yt was just a known sequence. Okay. So when we solved this before, and we have that u prime is positive and this is negative, I am now going to assume the special case of that. I'm going to assume u of c is equal to minus c bar squared. Actually, I'll do it this way. This. Yeah. So, yeah, if you check this out, you'll see where c bar is list consumption. I'm just assuming this is quadratic, and so u prime is going to be linear in C. That's a very special case, which I'm going to impose. We'll come back to that. Okay, whether or not I impose this, if I solve this problem, before we got, what did the person do? Completely consumption smooth. He said this equal to C bar, and we had a formula for C bar, and I want to put it right here. The formula we got for C bar was this was equal to beta inverse. Well, no, I'm sorry, that's not what it was. The formula we got for C bar was 1 minus beta F0 plus, actually, we got a formula that we could write like this. This was actually always true. It's equal to Ft plus summation j equals 0 through infinity, beta to the j, yt plus j. We got that formula. And this worked, this formula held for any t. We got that formula. If you don't remember that, we can go back and get it. But right now, I just want you to believe me that that's what we got when yt was a known sequence. Here, when yt is a random sequence, and this utility function is quadratic, The solution is to choose a consumption plan, CT, that satisfies this equation. And stare at this equation. Instead of making CT constant like it is here, instead we make CT equal to this, 1 minus beta this, but in place of this, right here, we're going to put an ET, where that's the mathematical expectation, right here. That's the mathematical expectation of the present discounted value of labor income. So the whole thing, we derive this equation simply by replacing the present value of income by its best forecast. And this is valid when U prime of C is linear in C. Otherwise, it's an approximation that ignores some effects that we might talk about later if we have time. So this equation is the stochastic version of Milton Friedman's consumption function. It's a generalization of it. So it turns out we can do some math with this. System 1 and 2. So what's 1? 1 is the formula for asset accumulation. 2 is the consumption function. If you combine those and do some work, 2 lines of algebra, you'll get this equation. That ft plus 1, you'll get equation 3. Ft plus 1 is equal to ft plus beta inverse, and then this expression here, yt minus this. It's a fascinating expression, because what you do is yt is your current income, and Milton Friedman defined 1 minus beta et this he defined that as your permanent income. And what did he mean by that? That's essentially the interest payment. That's this 1 minus beta, looks like an interest payment on the expected present value of all of your future labor income. So it's as if you're regarding yourself as an asset, and that's your asset value as a worker. You take the interest on that at that fixed interest rate, you call that your permanent income. And what this expression says is you look at the gap between your current income and your permanent income, and you add a fraction, which is beta inverse, the interest factor appears again, to your current assets. So if your current income is greater than your permanent income, most of what you do is save. If it's less, you borrow. And this term beta inverse is very close to 1, because the interest 1 plus because remember, it's a reciprocal of a discount factor. So this number is close to 1. So most of what you do, not quite all of it, is if your income is higher than your permanent income, you save and add to your assets. Otherwise, you dissave and run your assets down. And this is how you achieve your consumption smoothing. This is a key equation. Okay. Okay, this takes a little digesting, but this is close to an implication of math that we've already done. Okay, so these imply These imply the following. I'm going to do a little piece of mathematics now. It's just going to be algebra. And I'm going to get a striking result. So first I'm going to write down my decision rule at time t. That's what I did here. I'm going to write it down t plus 1. So I'm just going to copy it, but shift the time indices. And then I'm going to subtract it. If I subtract it, I get this. Okay. I get this. And now I just do some algebra. So I'm just going to reveal this algebra, and then I'm going to go to the punchline. So I do this algebra, I do a couple lines, I do a couple more lines, I do a couple more lines, and I finally get to this thing. Well, here, I went to the algebra. Yeah. I do this, I do all this algebra. Okay, I do this. And I get this. Get this equation right here. Now, if we stare at this, this equation is full of insight, because what it tells me is the only reason that consumption moves between time t plus 1 and t. Remember, this person wants the consumption smooth. But now, the only way consumption smooth is to save in terms of this, save or save in terms of this risk-free asset. So he's not going to be able completely to consumption smooth because he can't buy insurance. The only thing he can do is accumulate or decumulate assets. So he has an imperfect ability to consumption smooth, but he wants to consumption smooth as much as he can. So when does he or she move their consumption? What this formula says is only when the income, the expected discounted value of your income from time t plus 1 on is higher or lower than you thought it was going to be the previous period. So what you want to look at here is that's an expectation at time t plus 1. That's an expectation of time t. And what this thing is this is the news about your permanent income, as Milton Friedman defined it above. It's the news at t plus 1. Why do I say news? Because at t, you knew this. At t plus 1, you know this. Okay. So let's digest that for a while. Well, there's a proof. And I'm not going to insist that you look at the proof. You may if you want. It's just algebra. Just a little bit of algebra, and we prove this. There we go. So that's the end of the proof. But now we can actually do, we can actually see, we actually know how to form. If we hadn't had Mr. von Neumann teaching us, we actually know how to form this term and this term. So just remember, et plus 1, summation j equals 0 to infinity, beta to the j, yt plus j plus 1 is just this. It's g I minus beta a inverse. That came from the beginning, xt plus 1. And so that's what this is. And now I'm just going to take the conditional expectation I'm going to compute the conditional expectation of this thing at time t. So what that is, well, that's going to be easy because look, get it directly from here. G I minus beta A inverse, those are just numbers, those are fixed, and I can pass the conditional expectation inside here, but that just gives me G I minus beta A inverse A xt, which is this. So therefore, I can just do a little piece of math. I can just subtract those two to compute our key term. Remember, our key term is the news in the present discounted value of your labor income. And if you do that, you just rearrange. So I just substitute in and I do some algebra. I do some linear algebra. And when I do that, I do this line, I do this line, and finally I get this. I get that this thing is equal to this. So therefore, I get this beautiful equation. I get finally that CT plus 1 minus CT is equal to this. It's 1 minus beta times this thing. And this has an interpretation. Okay, so I'm going to this is a very general version of a very important theory of consumption. And what it says is this. This is some big matrix, H, which we just computed, ft plus 1. That's the punchline, where H bar is just exactly that. Okay. Okay, so now I'm just going to talk a little bit about this equation. We're going to stare at it. So we have CT plus 1 CT plus 1 minus CT, this is what we deduced, is equal to H bar epsilon T plus 1, where epsilon T plus 1 is normal, 0, I, and it's IID. So we could iterate this equation. Now we know something about this equation. So CT plus 1 is equal to CT plus H bar epsilon T plus 1. CT plus 2, what's that equal to? It's equal to CT plus H bar epsilon T plus 2 plus epsilon T plus 1. Blah, 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 blah. CT plus J is equal to CT plus H bar epsilon T plus J plus epsilon T plus J minus 1 plus epsilon T plus 1. Now, stare at this and ask yourself, if you're standing at T, what's the best forecast of xt plus j? So all you do, it's equal to et of ct, but you know ct, because it's today, plus h bar times the best forecast of this, which is 0, the best forecast of this, which is 0, plus 0. So the best forecast at time t of consumption, the best forecast of consumption at time t of ct plus j is just today's consumption. So this thing is consumption is a random walk. No matter what A, C, and G are. What that means is no matter what the labor income process is, consumption is a random walk. And that's the stochastic version, the random version of consumption smoothing that this person wants to do. Can't consume, he can't totally smooth his consumption, he just doesn't have the ability, but he'd like to. So the next best thing is to make consumption a random walk. And this is Robert Hall's famous version of the permanent income model of Friedman. Okay. So, here's what we're going to do now. We're going to talk about some of the things that we just did in class on Tuesday. And I'd like you to go over the notes so things fall into place. What I'm going to do now is show you another resource. I'm going to quickly go over it. So I'll tell you where I am right now. I'm on the, here's where I am. I'm on the internet. So I'm on this site called Quantico that you can get to. My friend John Stachersky and I put this together. So you go to the site and you go to lectures. And I'm going to do this. The lectures are in Python or in Julia. Those are two lectures. Those are two languages. I'm going to go to Python. And I'm going to go to a lecture that's kind of on the subject that we're talking about. There are several models of the it's called optimal savings, and these two lectures right here, optimal savings 1 and optimal savings 2, are what I can. So these three lectures here, I'm going to show you some things in class, and you can anticipate me. Okay, so here's where I click this, and I have this lecture comes up, and guess what? It's a permanent income model. And I'll just talk you through this a little bit because I want to show you some pictures. Punchline is I want to show you some pictures that I'm going to use Python. I'm going to generate using Python. That's where I'm coming. So, as I told you, we're going to have a rational expectations version of the Milton-Friedman model. And we're going to use this to do various things. So, as a preliminary, there's a little section here on what a martingale is. And what a martingale, when I use it, a martingale is a stochastic process X that satisfies this condition. The conditional expectation of X at time t plus 1 is equal to xt. If you satisfy that, you're a martingale. And it's sometimes also referred to as a random walk. They're not quite identical, but for all practical purposes in our class, if I say martingale, I mean random walk and vice versa. Okay. So a random walk is a special kind of martingale that's invented by Einstein. And here essentially it's going to look like this. Xt plus 1 is equal to xt plus wt plus 1, where wt plus 1 can't be predicted. there's a little mathematical nicety here, but we're not going to use that in this class. Okay, so now we're going to have a consumer. This is all going to look old, except for a minor change in convention. There's a consumer that cares about this. Well, there's our friend, but I put a conditional expectation at time 0 now to account for randomness. So all of these things are the same. I've written the budget constraint a little bit differently, but there's YT and there's CT. The timing is slightly different about when you receive the interest. This is essentially a version of our budget constraint. Okay. Not everyone writes the budget constraint in exactly the same way, and it just hinges on when the interest is paid on your current savings. Okay. We're going to assume that 1 plus the net interest rate inverse is equal to beta. That's Friedman's assumption. Again, we're going to have exactly, I guess we called it Z instead of X, but this is going to be our income process. We're going to assume the spectral radius. That just means that the maximum eigenvalue of A is strictly less than the square root of 1 over root beta. That's all it means. It means that the process isn't growing too fast for our discounted sums not to converge. Well, we say that. We're going to make the utility function quadratic, just like this. And we're going to impose a no Ponzi scheme condition, which we're going to write like this. There's a variety of them. This is a common one, that the square of your debt can't grow so fast that this quantity here becomes infinite. So then we just go through and we get first order conditions, and then which I'm going to come back to in another lecture very soon. First order conditions are going to be that the margin utility of consumption follows a martingale. And with quadratic utility or linear margin utility, that directly implies that consumption itself is a martingale. And that's kind of the result that we got earlier in the lecture. We're going to see that in several ways. Okay, so now the rest of this is just going to be repeating math that I just showed you. Here's our decision rule, which is it's a version of what I showed you before. Your consumption, this is Friedman's rule, is equal to an interest factor times your human wealth, that's what this term is, plus your non-human wealth. So minus B, B is your borrowing, minus B are your assets. So that's all just said here. That's what's in this lecture. The reason I'm showing this quickly is that this lecture is going to have just a review of what we already did. And it's going to have some more things. So guess what? This is going to look just like what we just did. This is going to look like what we just did. And then we can do some more things with this. So once we do this, and I'm going to be talking about this in class, we can find formulas that tell us, since we have a stochastic process now, which is a probability distribution over a sequence, we can compute means, covariances, and various things for that sequence. And that's what we do. So like, here's going to be kind of the punchline. We're going to create a process where income is IID. independently identically distributed. So it's as unsmooth, in some senses, as unsmooth as you can make it. What is this person going to do? And then we can kind of get some pictures. What this is what we've done is we've taken this math and we've mapped it into Python, which is a free, very nice computer language. And we give you the code. So the code looks almost like math. That's the code. So guess what? There's our formula for C. There's our formula for B, and so on. We just put this in. And then we're going to do a simulation. So this is what this is going to look like. So the green line is your income, non-financial income, and it's as random as it could be. See it moving like this? It's IID. I'm going to start the person off with 0 debt, and then what this person is going to do is going to smooth his consumption. The black line is consumption. That's following a random walk, but you'll see it's doing a very good job of smoothing his income because he wants to. He can't do it perfectly, and the way he's doing it is, well, what this person is doing is is running up a bunch of debt here. Look at this. He's running up some debt. Here he runs it down. Here he runs it up, runs up his debt. And then, the reason he's running up his debt is his income is less than his consumption. Every time this line is above this line, he's issuing debt, and this is heading north. Here he's got some big negative income shocks, so his debt runs up. His debt runs up above this, and now he's going to get some good income shocks. He's not going to use it to consume. He's going to use it to run down his debt. So that's what this permanent income model does for us. And okay, so what I want you to do is to look at this lecture yourself. What we'll do the next time in class is we'll start here. Actually, it would be great for me if you thought of some questions that you want to ask. So I am now going to thank you for coming to this lecture, and I'll see you next time.